speech volume. Can you hear me now? All right, so this learning the system up here. Okay, oh, that's better. Okay. All right, so I'm going to, well, first of all, any questions from the last few lectures? No, so a number of people have asked me about the extra labs, the so-called guinea pig labs, the ones that some students have volunteered to run through. There's probably 10 to maybe 20 students who volunteered to do this so far. And the question has been, when are these going to be run? And I can't tell you. I'm going to ask Lloyd or Tammy Mao is going to be organizing that and contacting you. I've been collecting your email addresses. But we want to run through them ourselves, so we ran through the first, partway through the first one, so we will be running through the second one as well, probably this week. But expect maybe middle of September. All right, so if you're one of these people and you're anxious to try out these labs, give us a little more time to run through the labs ourselves before and fix things before we run you guys through them. All right? Okay, so are there questions? So just to remind you where we left off last time, we were talking about Hardy-Weinberg, why do we care? And the first thing I told you was that, at least with just Hardy-Weinberg, the first result is that Mendelian genetics plus random mating means that the allele frequencies will not change over time. So the genetic variation is not lost just due to random mating. We'll talk about forces, evolutionary forces that do cause frequencies to change, but just random mating with infinitely large population sizes and Mendelian genetics, allele frequencies don't change. Okay? And then I was talking a little bit about human genetics, which is where humans, I thought, might care about human genetics. The first thing I did talk about was DNA fingerprinting, and what I want to talk about where I left off was on a discussion of rare diseases. Okay? And one result of Hardy-Weinberg concerns genetic diseases that only express themselves when you're homozygous, so rare recessive genetic diseases. So the example would be you have to have 2 copies of a particular gene for it to be to have the genetic disease. And a good example would be cystic fibrosis. Okay, and cystic fibrosis is a pretty high frequency, is the highest frequency in European populations, and it's caused by a particular allele called the delta 508 allele. Okay, it's a deletion allele. It's some amino acid position 508 in some gene. Okay, so it's a deletion mutation. When you're homozygous for that allele, you have cystic fibrosis. So individuals that are delta 508, they have cystic fibrosis. Okay. And of course, in order to actually be homozygous for this, you have to have parents who were at least carriers. They could either have had the disease or they could be carriers for the disease, which would be delta 508, and then we'll say wild type, the normal variant of the disease. These people are called carriers. Okay. So that's the situation. Have the disease, you're a carrier for the disease. What is the frequency of the delta 508 mutation in the population? So we'll maybe write that out as delta 508. It turns out it's about 0.02. Okay, that is the frequency of that allele in European populations, in the European population, I should say. So what does Hardy-Weinberg say about the frequency of carriers and also of cystic fibrosis? Well, cystic fibrosis, according to Hardy-Weinberg, would be what? What would be the frequency? It would be 0.02 times 0.02. That is the expected frequency under Hardy-Weinberg, just random mating, of people that are homozygous for the delta 508 allele. And that's equal to 0.0004, which is about, or is exactly 1 over 2,500. So the prediction with Hardy-Weinberg is that about 1 in 2,500 people will have cystic fibrosis just due to random mating in European populations. Well, how about the frequency of the carriers? So one of the interesting results of Hardy-Weinberg is that the frequency of the carriers is much higher than the frequency of the people with the disease. Okay? And I'll just introduce you to a type of trick you often see in the math of population genetics where we're dealing with often very low frequencies. So what is the frequency of the heterozygous individuals with Hardy-Weinberg? 2pq. All right, so q we'll say is going to be the frequency of the delta 508, which is 0.02, right? P would be obviously 0.98. Right? And 2 as well, 2. But here's the trick. Often when you're talking about, here we have a very small number, well, this number is going to be very close to 1. So if you want to do a quick off-the-cuff calculation of what the frequency of these heterozygous individuals will be when one of the alleles is very rare, just substitute 1 here. So the off-the-cuff answer of the frequency of the carriers is 2 times 0.02, which is 0.04, roughly 4%. So in the way you actually show that this is an approximation, so the frequency of that genotype is about 0.04. You use the squiggly equal sign. It's approximately about. And that's because we didn't go through the trouble of multiplying 2 times 0.98 times 0.02, which isn't that big a deal, right, also. But you find out if you do that, that it's about 0.04, right? I'm sure some of your calculators might be doing that. So the frequency of the carriers is roughly twice the frequency of the allele, and the point here is that that's actually, the frequency of the carriers is pretty high. Roughly 4% of the people of European descent are carriers for cystic fibrosis, even though the disease itself is quite rare. Right? I would say 1 over 2,500, although it's an unfortunate number, is fairly rare. Okay, so that is one result of Hardy-Weinberg, is that carriers are much more frequent than people with the actual disease, for cases where the disease is recessive. That is to say, you have to have 2 copies of the allele to have the disease. Okay. And there's also ethical issues that are associated with this as well. I mean, we can now test for all sorts of diseases, including cystic fibrosis, so you can easily determine whether you are a carrier or not for that disease. Right? So I put ethical issues as a separate line here. This is not a class where we can resolve these types of problems, but do consider that these days you have the ability to easily test yourself for all sorts of rare genetic diseases and your future mate spouse as well. Right? And so these types of questions might be of concern to you. Right? And these types of questions become much more prevalent now that we can actually have the technology to easily and cheaply determine whether you're a carrier or not. You can do this yourself anonymously with some of the genetic tests that are out there today. Right, I was going to talk about ApoE as another example of a disease that's it's a gene that's highly associated with Alzheimer's. Sometimes these diseases aren't all or nothing. If you have 2 copies of delta 508, you get cystic fibrosis. Well, there's other genes, other diseases where you're just at a higher risk for the disease. It's not a certainty. So, for instance, there is an allele for the ApoE gene, and the allele is called ApoE star 4. That's the name of the allele. Remember, if you're the person who discovers the allele, you can call it whatever you want, right? So, and other people can't argue with it. So there's the name of the allele. And it turns out that people who are heterozygous for this allele have a 3 times risk factor for developing Alzheimer's over their lifetime. Okay? People who are homozygous for this have a 15 times increased risk factor over the general population for developing Alzheimer's. So this is a case where it's not nearly as clear what if anything, you can do about it if you discover this, right? This is a disease where you're not certain, even if you're homozygous for the ApoE4 allele, you're not certain to get the disease. You're not certain to develop Alzheimer's when you become old, right? So it's not always cut and dry, what to do with these types of information. But you can also predict the frequencies of these different genotypes using Hardy-Weinberg. Okay. So that is what I wanted to say about ethical issues. I want to go on to the last point I want to make is, Hardy-Weinberg, for the most part, if you think about it, is kind of boring, right? And I gave you some exciting reasons to be, I tried to make you excited about Hardy-Weinberg with these other examples of how it's actually used. But for the most part, it's like what happens when nothing interesting is happening, right? That's basically the story of Hardy-Weinberg. So Hardy-Weinberg is important for one last reason, and it's a practical tool. Hardy-Weinberg forms what you might call a null hypothesis in population genetics. So if you've taken statistics in high school or here, you know what a null hypothesis is and how it's used in statistics. But generally speaking, it's the hypothesis that's being tested, the idea that's being tested. So if you have Hardy-Weinberg as your null hypothesis and you have some data, maybe some human genetic data from a large number of individuals from some population of humans, you can actually test different genes to see if their genotype frequencies are in Hardy-Weinberg. It's a statistical test. In this class, I mentioned that when I actually give you questions regarding Hardy-Weinberg and I ask are the frequencies in Hardy-Weinberg equilibrium, it's a yes or no type of result, right? They'll either be precisely to an unlimited number of decimal places exactly in Hardy-Weinberg, or they will not be. But in real life, people apply a statistical test. They realize that when you have a finite sample of individuals and you genotype them, that there's going to be at least some small fluctuations around Hardy-Weinberg equilibrium, even if all the assumptions of Hardy-Weinberg were satisfied. So you perform a statistical test. And when you reject the null hypothesis, when you say no, the genotypes are not in Hardy-Weinberg, what does that mean? Well, it means something interesting is happening at last, right? It means that something such as natural selection or some other process is causing the genotype frequencies to not be in Hardy-Weinberg equilibrium. And here's a couple of examples. So here's an example from wild oats. All right, there's a particular gene. It's not really important which it is, but the genotypes they're going to be often in our class will be big A, little a, little a. And here's the frequencies of those genotypes, 0.548. These were the observed frequencies. Somebody went out and surveyed for this particular locus the genotypes. And found that almost 55% of the individuals were homozygous for the big A allele, about 7% were heterozygous, and about 38% were homozygous for the little a allele. These are the observed frequencies. All right, these are actually observed in nature. So we can go ahead and ask whether these frequencies are in Hardy-Weinberg or not, yes or no. So we need to calculate P and Q, which we'll call the frequency of the big A allele, the frequency of the little a allele. I told you guys last time how to do that. We can easily calculate the frequency of P, the big A allele as being this frequency plus half of this frequency. And we're only given frequencies, so that would be 0.58. And then the frequency of these guys will be 0.42. With me so far? Okay. So what are the Hardy-Weinberg expected frequencies for these three genotypes? Well, it's 0.58 times 0.58 for the frequency of the big A alleles. That gives you about 0.34. It's going to be 0.42 times 0.42 for the frequency of the little alleles. That's about 0.17. And then the heterozygous individuals' expected frequencies is 2 times 0.58 times 0.48, which is 0.49. Now, I'll tell you the first result is that these expected frequencies are statistically different than the observed frequencies. Right? The sample sizes were large enough that the statistical test says that the null hypothesis that the frequencies or the genotype frequencies are Hardy-Weinberg equilibrium is rejected. Okay? And the interesting thing you'll note is that we observe many more homozygous individuals than we expect right? Hardy-Weinberg says that we should see 34% of the big A homozygous individuals, and we should see 17% of the homozygous little a individuals, and yet we see many more homozygous individuals. Okay? So something is going on. They're out of Hardy-Weinberg, so at least some of the assumptions of Hardy-Weinberg are not satisfied. And then the question becomes, well, what is it? What is causing these allele frequencies, these genotype frequencies, rather to be so out of whack with Hardy-Weinberg? And the interesting result is that you can actually survey many loci in wild oats, and you find that many loci have this pattern where you have many more homozygous individuals than heterozygous individuals than expected. Okay? And so you can say, well, is it natural selection? Well, the natural selection would have to be operating pretty strongly on many different loci simultaneously. Turns out that in this case, you don't have to look very far. Wild oats self. All right? So what do I mean by self? It means that they mate with themselves. All right? So when you have that type of mating pattern, when you're self, then one of the results is you have many more homozygous individuals being created, many more homozygous individuals being formed. And I will also point out that Hardy-Weinberg assumes random mating, and this might be obvious to you, but mating with yourself is not random. All right? That's pretty clear. All right, so that's one example. Example 2 is one we will refer to later as well. And this has to do with sickle cell anemia. It's a disease that's caused by being homozygous for the sickling cell allele, SS. Normal variants we'll call it big A, and then you have heterozygous individuals as well. There's actually a specific mutation that causes the sickle cell anemia. So this is an allele at the beta globin gene, one of the proteins that's involved in carrying oxygen. And the S allele, this S allele is caused by one amino acid replacement in that beta globin gene. One amino acid replacement. So it's a change from glutamate, which is one of the 20 amino acids, to valine at position 6, the 6th amino acid, which is normally glutamate. For these S alleles, it's valine. That's all. That's a single mutation, single amino acid difference in those proteins. Okay, so that's a little bit about the biology. So there was a survey of about almost 31,000 adults who lived in equatorial Africa. Okay, so this is the results in terms of the raw numbers of these different genotypes. There were 25,374 individuals that were homozygous for the normal variant of the allele. There were 5,482 individuals who were heterozygous, and there were just 67 adults who were homozygous for the sickle cell allele. And just to point out the total number, I'm just going to do the sum here, is 30,923. That's the total number of people that were surveyed. So once again, these are the observed counts now for these different genotypes. All right, so P and Q, we'll say Q now is the frequency of the sickle cell allele, the S allele. And I'm just going to give you the results since we don't have a whole bunch of time. But how would we calculate this? Well, I would use the other easy method I described in class. Just because you have the counts of the alleles, you know the total number of individuals. The total number of alleles is twice that, right? It's roughly 62,000. So you should be able to calculate the allele frequencies from these observed counts. You should make certain you can do that. Okay? So those are the observed allele frequencies. Let's go ahead and calculate the Hardy-Weinberg frequencies. The Hardy-Weinberg frequencies for the big A allele is 0.91 times 0.91, which is 0.83. And for the heterozygous individuals, it's 0.16, 2pq. And then you have 0.008 for the last genotype, the SS genotype. Now, the problem here is it's difficult to compare frequencies to raw counts, right? So you have two choices here. You could convert these observed counts into observed frequencies, and then you'd be able to directly compare the observed frequencies of those genotypes to the Hardy-Weinberg expected frequencies. Or we can do the opposite. We can just multiply each one of these numbers by the total number of individuals. That would be 30,923, and we'd be comparing an expected number of individuals to the observed number of individuals. So I'll do the second, just because it's different, right? So if we go ahead and multiply each of these numbers by 30,923, we get 25,666.1. We get 4947.7, and we get 250.5. So these are the expected number of people if Hardy-Weinberg, if the population were in Hardy-Weinberg, the expected number of individuals of each genotype. And you shouldn't get thrown off by these fractions. It's kind of like the statement you probably heard that the average American family has 1.8 kids. It's not like they have a whole kid and 0.8 of a kid. That's gross. This is just the expected number. On average, it's an average. Okay. But the point here is that these are the expected frequencies, and you might look at these and say, well, you know what? By the eyeball test, which is always a bad statistical test, but the eyeball statistical test, you might say, well, they don't look very different. But it turns out they are. They're statistically different. If you apply a statistical test to these results, you'll find that the observed frequency, the observed counts are out of Hardy-Weinberg equilibrium. And one of the reasons why a statistical test would say that they're different in this case is because the sample size is so large. Generally speaking, when you have a larger and larger sample size, you have more and more power to reject a null hypothesis. Right? That's just a standard result in statistics. But the cause here is not non-random mating, but rather natural selection is operating differently on these different genotypes. Okay? So the first thing I should say is that these counts were as adults. So the idea is that the children, because humans more or less mate randomly, the children were probably in Hardy-Weinberg equilibrium, right? But then you've had differential death to adulthood. It turns out these individuals, the ones that are homozygous for the sickling allele, are very sick individuals. Right? They're very sick individuals, and they don't tend to survive as well as people that don't have that are not homozygous. The other result is that even though the count doesn't look quite, you notice that we have many more heterozygous individuals than you'd expect under Hardy-Weinberg. Okay? And the reason is that these people have a fitness advantage. All right? And they have a fitness advantage only in the presence of malaria. Right? Remember, this population, these people were sampled from equatorial Africa, where malaria is a major cause of death among people. Okay? And so it turns out that the heterozygous individuals are somewhat protected from malaria. All right? These people suffer malaria at the normal rate. These people are just sick individuals. These people have a fitness advantage in the presence of malaria. Okay? Now, if you take them away from the malaria, or if we're ever fortunate enough to actually remove malaria, eradicate it from Earth, then these individuals will not have a fitness advantage anymore. So note that the genotype fitnesses are context dependent. They depend upon the environment. Okay. So that is the last thing I wanted to say about Hardy-Weinberg. I know I spent a lot of time talking about it, but it is an important idea. Even if you're not excited about it, I hope you can be a little bit more excited about it. Now, I want to turn my attention to the other more interesting things that can happen in populations. What are the evolutionary forces that do cause alleles to change frequencies? All right. So evolutionary processes that can change allele frequencies in a population. Well, the list is small. There's 4 things. Right, here they are. Let's cut to the chase. One of the forces is mutation. Another is natural selection. Another is genetic drift. And the other goes by the name of gene flow, or sometimes migration. Okay? Each of these forces can cause alleles to change frequencies in a population. And maybe I should draw my idealized population again. Here we are. So this population has individuals that are so forth. So what are these forces and how do they affect the frequencies of an allele? Well, mutation is simply the changing of an allele from one form to another. By definition, it has to change the allele frequencies. As an example, I didn't draw it this way, but let's imagine that all these individuals were homozygous for the big A allele. Right? Well, if you had a single mutation then in this population that changed one of these big A alleles into a little a allele, a different form, the frequencies have changed. Right? What is the frequency of the little a allele when it first occurs? Well, this mutation lands on one chromosome in one individual. Right? So it's initially there's one copy of it. And how many individuals are in the population? Well, we've been using the symbol n for the number of individuals. Is that its initial frequency? No, right? Because this n is not the number, this is the number of individuals, the number of alleles in the population, because every individual has 2 alleles is 2n. So it turns out that every mutation out there has this as its initial frequency, as its starting frequency. When it first occurs, it lands on one chromosome in one individual, its initial frequency is 1 over 2n. But that's, so you can see that initially, mutations by definition have to change the allele frequencies from 1 to 1 minus 1 over 2n for the big A allele, and from 0 to 1 over 2n for the little a allele, right? That's a small change, but it's a change, right? And I should mention too, while we're on the subject of mutation, that mutation is the ultimate cause of all genetic variation in a population.